It's great to see such a full house. So welcome, everybody. This is the Kronos Slang booth. Slang is our newest initiative at Kronos. It's a modern shading language, and it's not just interesting technology. It's the first initiative that Kronos has organized as an open source project rather than an open standard. And so we're very fortunate today to have Shannon Woods from NVIDIA, who's the chair of the Slang Working Group, who's going to explain all the cool stuff about Slang and why we're organized the way we have. So Shannon, over to you.
Thank you so much, everybody, and thank you, Neil. So if I were to give you a problem statement for Slang, it would be roughly this. The needs of shader developers today are much different than they were when languages like GLSL and HLSL were originally created. The shader code bases in use today are orders of magnitude larger than 10 years ago and more complex. Developers need to deploy their code to several different platforms and have it work the same everywhere. There's a combinatorial explosion in the number of shader variants that must be compiled, leading to painful compile times, binary sizes, and load times. While that's been with us for a while, it only gets worse as the complexity increases. We also need to expose functionality for new innovations in graphics, especially as neural techniques start becoming more commonplace. And at this critical juncture, GLSL is no longer innovating new features. It's only playing catch up. Enter Slang. So some folks in the room are probably familiar with the project, but to give a very brief overview for everyone else, Slang is a shading language and a compiler that ingests that shading language and outputs to a number of different formats for use across different APIs and platforms. Slang's syntax is quite similar to HLSL, but with a good number of additional language features, which I will go into in a later slide. Slang also provides helpful on-ramps into Slang from HLSL and GLSL. It is able to compile most HLSL and GLSL syntax as is. One of the key parts of Slang's philosophy is that when compiling to any of the various backends which it supports, we want to expose the full capabilities of the target to the user, rather than just providing the subset of what is available across all of the targets. For example, if you're targeting HLSL, ray tracing is available, but if you're targeting WGSL, it is not. In addition to generating shader kernels themselves, Slang also has capabilities for generating the binding code necessary to use them from PyTorch, which can save developers a lot of time writing glue code. We've got some additional improvements we're hoping to add here in the near future as well. And the latest development for Slang is that we're now part of Kronos. So Slang began development more than a decade ago as a collaboration between NVIDIA and Carnegie Mellon. And this fall, NVIDIA donated the language and the compiler to Kronos so that it could be managed collaboratively. This doesn't mean NVIDIA has pulled back any of its engineering support. In fact, we've increased the number of engineers working on Slang even more. So we believe that a diversity of shading languages in the ecosystem encourages competition and innovation. If we take multiple approaches to solve a problem, we can provide developers with options and collectively converge upon a set of solutions that are optimal. We also think it's important that there should be language options which are actively evolving under the influence of multiple voices rather than a single corporate entity. GLSL once occupied that space in the ecosystem, but GLSL development has stymied in the era of explicit graphics APIs like Vulkan. We think that Slang can provide even more value because it can be used as the shading language across all the modern graphic APIs, as well as for GPU applications. And I want to emphasize that Slang is by developers for developers. Slang's community management policies are intentionally built for technical work to happen completely in the open, using best practices from the open source software community. Contribution is open to any interested developer, not just Kronos members. And not just, oh, here's a bug fix, but truly having a voice in the language development. We've documented the processes for becoming a committer and a code or language owner on our website. The links will be provided in the slides. We also do our technical debate and decision making in the open on Discord, where anyone can observe or join. You can hop on right now and provide input to the discussions where we're figuring out our priorities or get support for upstreaming your own custom backend. Essentially, if there is a problem that you wished your shading language could solve, you can join us and work to get a solution added to Slang. To put things in a more easily comparable format, we think Slang is awesome because it provides modular code management, automatic differentiation, deployability to diverse targets, an open source compiler, and open governance. And we think it's awesome because it complements the other shading languages in the space. We're taking a different but complementary evolutionary path, and we think developers benefit from having those choices. So if you're interested in that little asterisk by the no, I have another slide that can maybe explain it. So a lot has changed since the legacy C++ days, and languages across the ecosystem, including C++, are learning from some of the choices that C++ made way back when and pursuing more modern language structure. While Slang originally shared syntax with HLSL, the way that Slang and HLSL are pursuing modernity aren't exactly the same, and we think that's a good thing. HLSL is converging closer to modern C++ and leveraging the tooling that's available in that ecosystem, while Slang is making language choices closer to those of Swift or Rust. Now, I've just talked a lot about why we think it's important to do technical development in the open and why it's important to have multiple voices in the room when we do it. And we think this is one of the things that makes Slang different. But that's all kind of abstract. And there's also plenty of concrete, meaty features that Slang offers that we think make it stand out and that are a result of our open development approach. In practical terms, one of Slang's biggest strengths is diversity of its target platform support, which I mentioned earlier. Because the targets are supported by the Slang compiler itself, you get a single coherent solve instead of having to pipe code in and out of several open source libraries and dealing with the rough edges in between all of them and the inevitable mystery bugs that crop up. Slang also makes management of code across a bunch of different backends much less of a headache to debug and maintain because it preserves identifier names and avoids a lot of the munging of code that makes it very difficult to debug a ball of spear V that emerges at the other end of an arcane pipeline. One of the coolest features that is unique to Slang in the shading language world is automatic differentiation, built right into the language. I'll go into some more depth on autodiff later in the presentation and even show some examples in action, but the very, very brief summary is that you can write an arbitrary function and the Slang compiler will automatically produce the differential version of that function. This is particularly useful for using gradient descent in ML training, for example, in 3D reconstruction. And then those modern language choices that I talked about, Slang's approach to modularity and polymorphism are aimed squarely at the long-standing problems in the shading language ecosystem around shader combinatorics and compile time explosion. Now, just to re-emphasize, Slang's support for all of these target languages is a one-stop shop. There's no need to chain together Byzantine pipelines made of different tools, maintained in different places, and at different scales. And because of that, the tooling just works. Slang is also able to keep your code human readable through the pipeline because it preserves information about the original code structure and identifier names. Now, the newest target that Slang has added is support for WGSL, which is the shading language that powers WebGPU, the newest graphics API available on the web. And thanks to some of the groundwork already in Slang, adding this target was pretty straightforward. The first lines of WGSL support landed in the Slang compiler in September, and we've now got fully functional support. The really cool benefit of this particular target is that it enabled us to put up a live Slang playground so that you can enter your shader code and see the visual results right in your browser without needing to download and set up the Slang compiler if you just want to start playing around. This also means that Slang can be built on top of WebAssembly using Inscription, and with compression, we were able to get it down to just a 5 megabyte package. That means that it can be loaded in under 2 seconds, even on an excruciatingly slow mobile connection. And because the compilation is happening entirely within your browser, you can iterate and make changes and see the result without having to send any code up to a server anywhere. You even get language server support right in browser. And there are some really cool demos up there for you to tinker with. And in a few minutes, I will tempt the live demo gods by showing a live demo that digs into some of the more fun parts. But that's not our only new target. Slang also now has support for metal. This is, again, relatively new. We first started adding metal support in late summer of this year. Now, it's worth noting, Slang currently in metal supports vertex, fragment, compute, mesh, and amplification shaders, but ray tracing support isn't in just quite yet. The Slang compiler performs a number of automatic transformations to produce legal metal shading language from your input Slang, which enables the compiler to support some things even though there's no metal equivalent. For example, combine samplers or pointers to vector elements. You can see the transformations, all of them, that the Slang compiler performs for metal documented on our website, which is linked here. You can find the slides after the talk. And just like in our other backends, Slang adds line directives so that you can follow any errors back to the original of Slang when you're debugging. So one thing to mention while we're on the topic of debugging with Slang, support for Slang already exists in a lot of the tooling that you are using today. For example, you can do step-through debugging of Slang in RenderDoc, thanks to Slang and RenderDoc's support for non-semantic debug info. You can also do direct shader inspection in NVIDIA's Nsight tool and follow the shader transformations all the way from the Slang level through SPIR-V to shader assembly. It's also easy to get Slang. The Vulkan SDK includes it as a version 1.3.296.0. Spencer Fricke is going to talk about the Vulkan SDK in a bit more detail at tomorrow's Vulkan BOF session, which I believe is right here in this room, if you want more details on that. And I also mentioned that generics and interfaces enable things like IntelliSense to provide better developer guidance. You can make use of this today with the extensions available for Slang support in Visual Studio and VS Code. The language server module is provided with Slang, so it should also be possible to integrate support easily into any other IDE which supports the language server protocol that is also available on the Slang playground. And you can see the IntelliSense in action in our lovely animation here. You get autocomplete and all that fun stuff for Slang. But one of Slang's greatest strengths, usable across all of its targets, is its support for automatic differentiation. Now, differentiable functions are at the heart of the gradient descent approaches to optimization, which are showing up increasingly across the graphics world. For example, in 3D scene reconstruction or differentiable path tracing. But before now, performance critical, real-time, differentiable code had to be written by hand, meaning you have to write and maintain two copies of your shaders, the original shader and its differential. Now, any changes that you make to one have to be made correctly in the other. This is a headache that people are willing to put up with in research, but it poses a big maintainability problem in production. But support for automatic differentiation is built into Slang. It's a first-class language feature. Simply put, what this means is that you only need to annotate your function as differentiable, and Slang can automatically generate both the forward and backward differential forms. And Slang is able to produce code that's equivalently performant to hand-tuned CUDA code. This is huge. You don't have to sacrifice maintainability for performance or vice versa. And if there are parts of your algorithm which benefit from specific optimizations, Slang provides the flexibility for you to define custom derivatives for just the parts of your algorithm that benefit from it and still allow the rest to be automatically differentiated. This is also pretty cool because it enables a shared ecosystem between machine learning code and existing rendering systems. The Slang code that you write for training is the same code that you would use for rendering. And you don't have to take my word for it that Slang provides a benefit to differentiable and neural rendering code. George Kobenis, one of the authors of last year's 3D Gaussian splatting paper, created a Slang implementation of the rasterizer from the paper because Slang provides significant benefits in maintainability and allows him to use a single shared code base between the training and production renderers. And the Slang versions of the kernels match the performance of the handwritten CUDA, but using autodiff, making the system straightforward to implement and maintain. You can see the difference in maintainability just by looking at the difference that Slang makes in code length. The Slang implementation takes about 40% fewer lines of code than the handwritten version. While we're on the subject of performance, Slang has a lot to offer here. It's not just in the runtime. Slang can also help you address compilation time worries as well. Slang is within 10% of the GLSLC and DXC native compilation times when you give it the same monolithic shader code that you're used to using. But if you make use of Slang's modules, you can skip a significant chunk of the time that you would otherwise have to spend on semantic checking. In some of our internal benchmarks, this amounted to about 16% of the overall compile time. Now, I'm going to zoom in a little further on modules, generics, and interfaces because while these are common concepts outside of shading languages, they're new to this space. So modules provide both separable compilation and visibility control. And the reason that this has compilation time benefits is that you compile a module once and then reuse it from multiple places. And visibility enforcement makes sure that code is used safely and coherently across the code base, which is a big benefit when you might be working across a large team. Slang also provides generics and interfaces, which are the modern approach to parameterized polymorphism. These allow type checking to be done on the generic rather than only on the type substituted version of the code, which not only reduces the amount of redundant work that the compiler must do, but also enables developer support like IntelliSense to provide more useful feedback as you code, because it can make better deductions about how a generic type may be used. So if all of this sounds great, but you're worried about the difficulty of switching to Slang, don't worry, it's not hard. And you don't have to take my word for that either. Some big code bases have already made the move, including Valve's Source 2 engine, which replaced all of their HLSL with Slang and is now in use in production. They did this with minimal code changes, only about 10 lines in their entire HLSL code base. Autodesk is also putting Slang to the test in their Aurora path tracing renderer, both for Vulkan and Direct3D. The team reported that ray tracing was trivial to get working on both platforms in Slang. And Slang is pain-free in other ways as well. Just an 8 megabyte binary gets you support for all of Slang's targets, which can be further compressed if you're using it in a bandwidth-sensitive use case like the web. Slang has no dependence on LLVM. For CPU-side code, we generate C++. And the runtime performance, as I mentioned earlier, is able to meet or beat handwritten code, even when using fancy features like generics or dynamic dispatch. So one of the things that we've gotten questions about from time to time is about how templates interact with Slang, because that's one of the areas where Slang syntax differs, because Slang chose to go with generics. The good news is that the most common template use case is trivially portable to Slang. All you need to do is replace template with generic, like in this case here. But there are some more complex use cases for templates where a simple solution isn't enough. In a case like this, where the function calls one of the member functions of a parameter of generic or templated type, the templated case doesn't contain enough information for the compiler to guarantee that the member function actually exists until the type has been expanded. That's not a problem for templates because type checking happens on the expanded code. But with generics, the type checking happens on the generic type. So in order for this to be valid Slang code, you must provide information about the type constraint. This is still a pretty simple switch. You can create a simple macro which allows the same code to be used as a template in C++ or a generic in Slang using the where clause for situations like this. Looking a little bit closer at how this early type checking works for generics with an example, because the compiler has the information here that any generic type which conforms to the IEvaluable interface has an eval member function, you can define a function that takes a parameter of a generic type, require that the parameter's type conform to IEvaluable, and then evoke eval from inside the function. And IntelliSense can tell you before you even compile that it would be an error to pass a variable of type X, which does not conform to the IEvaluable interface. And that's pretty cool when you compare it to templates where you don't run into problems until the code has been expanded, and you may or may not wind up with an error that's about 3 pages long and full of angle brackets. So essentially, this is what the future could be like if your compiler supported early type checking on polymorphic types, and Slang does. So I invite you to try Slang out in your browser. The URL is right here, but you don't have to do it yourself. because I am going to do it for you. Or I'm going to try. There we go. The live demo gods are smiling upon me. Now, the tricky part is that I'm going to have to do code editing over there on that screen, so bear with me. So just to give you an idea of what you're looking at here, the main pane, which I can bring my mouse over, there we go. The main pane over here is full of your source Slang code. Down below is where compiler errors will show up. You're probably familiar with that paradigm from other IDEs. Up here in the upper right, you have the visualization pane, which, that's what your shader actually draws, if your shader draws something. And then down here, you can see the target code. Right now, it's WGSL because we're executing on top of WebGPU. And then in addition to the target code, you can actually also, this is pretty newly added, and I'm very bad at clicking on on touchpads. But this is the reflection in JSON format, so you can examine all of the attributes of your objects here. One of the other cool things, so your UI up here, there's a pull down menu where you can see a bunch of preloaded demos. You can run each of them, but you also get this set of controls over here, which allow you to choose a specific backend target if you just want to compile the Slang and see what the resulting GLSL or HLSL or what have you might be. And you can see here in the output HLSL, for example, that there are line directives emitted so that you can identify where in your source Slang code any part of the HLSL, which might be tripping you up, occurs when you run into it in your debugger. And you can also see that the identifier names here are preserved, although decorated. So it should be a lot easier to debug than the somewhat random and or obfuscated symbols that you can get out of other shader pipelines. One thing also to note is that for targets like GLSL or HLSL that only support a single entry point per shader blob, you'll get to choose which function is the entry point from this dropdown. And then this is one of my favorite buttons. I'll demonstrate how this works by taking you back to that lovely circle. Now, say I like this wonderful circle. It's a port of a shader that's available on ShaderToy, but I really like the color red. So I am going to, oh gosh, it's hard to see. I'm going to attempt to turn it really red. Yeah, it's going to be really red. So yeah, rerun the shader with lots of red. And if I want to share this version of the shader, so I've copied the link to the clipboard, and I can paste that in here if I remember how to paste on Windows. Yeah, that's a great Earl. So if I sent that to my friend, they would get my lovely bright red shader because I've sent them that shader embedded in the URL. Now, this is still done without uploading any shader code to a server anywhere. That shader is entirely contained in the URL. So there are a bunch of demos available here. We've been adding a bunch of them recently, so you can expect this set of things to expand. There are currently 3 main sections up at the top. These are kind of like system interaction things that show you how it works when you invoke a print from Slang, or just load an image from an URL. Down here at the bottom, these are kind of simple tutorial-like demos that show you how to use some of the features available in Slang. Like this one demonstrates how to use generics, interfaces, and extensions. So those are great if you are trying to learn your way around a feature that's available in Slang. but not some of the other shading languages, and you just want to see how it works. But my favorite, obviously, are the ones that draw pretty pictures. So we have a handful of those. This one is also a port of a shader available on ShaderToy, but we've changed this one a little bit so that it makes use of Slang's automatic differentiation feature. So it's a little hard for me to see from over here, but you can see, I think it's Wave DX or Wave something. Anyway, this is a function that is used by the normal calculation, which is like down here somewhere. There's normal. So you can see the normal function, which calculates the wave normals, invokes backward diff on the get waves function. And one of the cool things here is get waves is actually a generic function itself, and it takes in this number of iterations essentially. So I can fiddle with the number of iterations if I want to change the output of the wave format and actually change, I believe, how much how deep my backwards differentiation passes go. So if I wanted to tinker around with that, I could say, oh, 37, that's a lot. So I want just 3 iterations. 3 iterations should be enough for anybody. So I can rerun that. And now my shader runs faster, but it's kind of smooth. So maybe I didn't actually want to change it. Maybe I want a lot of iterations. That's a ton of iterations. That's surely going to look really cool. Oh no, it's very slow now. Don't do that. So, but you can see that the way that this is invoked. Oh, good, I just killed it. It's black. It's really fast now, though. But this wave calculation function is marked as differentiable. So this is the function that Slang is automatically calculating the differential for. And if I dig through all of this, I can find the differential form which Slang has created and output in WGSL. Now you might be like, well, there is a non-differential form of that shader that worked just fine. So why would you want to add automatic differentiation to it? We've got a bit of a cooler set of examples, which looks really weird if I leave a code window big like this. There we go. So this one itself is not being automatically differentiated. This one is just sort of a building block on which the automatic differentiation or automatically differentiable Gaussian splatter demo is built. This one, all it does is it is randomly generating a bunch of 2-dimensional Gaussian splats. They're less exciting than 3-dimensional Gaussian splats, but they're still pretty cool. It's just generating a random location, sigma, and color for each of the splats. And the way that that gets used in our differentiable 2D splatter demo is that essentially a bunch of random splats are created, and this example uses essentially a 2D form of the 3D Gaussian splatting algorithm to get all of those splats to converge on this nice image of a Jeep. And if I let it sit here for a really long time, it'll get quite fine-grained. I'm not going to dive into this code because there's 1,000 lines of it, and you have better things to do than have me read it to you. But if you want to go online and check out the 2D Gaussian splatting demo, that's the one that you want to look at. The Jeep's looking kind of cool now. All right, so anyway, now the tricky part is switching back to my my slides. Way harder than partial differentials. Okay. So yes, we know we did a log demo. So there are, I talked a lot about how Slang is built for open community involvement. and how we want to drive decisions based on the needs of the developers who use and contribute to Slang. So here are ways that you can get involved today. We have a Discord. There are 180, actually there are more than that now, members and counting. The discussions going on there are lively, and it is the communication method for the day-to-day developers of Slang. So if you want to weigh in on how great or how terrible a feature is, you can just come and discuss it with us right there. You can also file an issue on our GitHub or a feature request, start a discussion on GitHub, submit a pull request when you're ready. And we, like I mentioned, we have documented the process for becoming a trusted committer or even a code or language owner. And then over here on the right, this graph excites me a lot. This is the number of stars on the Slang, DXC, and GL Slang repositories. You can see Slang is now up there with its peer compilers, with a bunch of people getting engaged and doing exciting stuff. So here's my slide full of resources for where you should go and how you should get more information. Please join us. We're really excited to hear from you and get your input on the decisions that we should make for the language and how we guide it to be the best it can be for the ecosystem. And that's all I've got. So I'm happy to take questions if anybody has any. I think there's some microphones set up, and Lacey will. There we go.
Thanks for the great presentation. And I actually have not heard of Slang before SIGGRAPH Asia, and this sounds really exciting. So I have actually two questions. One was about how the PyTorch integration works. Does it work by generating CUDA code? And the other question was, I didn't understand how that shader type example with the Gaussian slats was able to fit Gaussians, because I thought shaders are usually stateless, right? So how does it remember the past state and stuff?
For the second question, there is a particular trick that's going on, and I think it's well commented in the code. There's a particular trick that's going on where you don't actually have to store the state. In fact, if you that demo uses the functionality in Slang where you can provide a custom derivative for part of your algorithm, because the automatic differentiator doesn't know that you don't actually need to save state when you're rolling back splats. It can avoid that and speed up the algorithm a lot. I am not well versed in that particular example enough to explain how it does it, but if you go on the Discord, Sai is the person who implemented that one, and that's the guy you want to ask. For the other question, I spent too long answering your second question and I've forgotten what it was. So can you repeat it?
My question was, how does the PyTorch integration work?
Right. So there's kind of two pieces to this. There's generating the kernels themselves, where you actually want to output CUDA code. The PyTorch integration it can actually generate the glue code that lets you invoke the kernels from PyTorch. My understanding from the folks working on the Python side of this is that they're planning to change up the way that we do this in the near future to make it a little bit more streamlined, because I think there's some things that have changed about PyTorch since it was originally written. So I think that code is going to get even more streamlined. But you can get tons of detail from the people who have implemented it themselves on Discord. I can only really give you the high level, but hopefully that's helpful.
Sorry, one more question. You mentioned that ray tracing support is coming up. So when it comes up, would we be able to write ray tracing code in Slang and then cross-compile it for both optics and let's say Vulkan ray tracing?
So ray tracing is available in. I know it's available in Vulkan. I know it's available in HLSL. I'm not super familiar with the optics backend myself, so I'd have to ask somebody else about that one. The only place I know that ray tracing is currently missing is on Metal, and that's because Metal's ray tracing paradigm is significantly different from the other APIs. So we want to go about implementing it in the right way, and it just hasn't been a priority for us yet because none of our Metal users have needed that yet. But it is something that we're thinking about and want to get right.
Thank you for your presentation. I have two questions. First one, why is the name Slang? It's kind of hard to Google. You always have to add a shader for it.
To answer that question, well, I am unable to answer that question because it was named quite a long time ago, and I was not yet working on Slang at the time. But by the time that we were basically moving Slang out of research and into production, it had existed long enough, and there were enough references to it, and a VC package, and a bunch of other things that changing the name actually would have made it also hard to find us because there were a lot of people who already knew us as Slang. So yeah, I am definitely aware of the Google problem, but Slang is our name.
Yeah, the second question, you mentioned that you can download class package for the compiler, but wouldn't it make more sense to precompile shaders and not ship the compiler to the users?
Sorry. Can you repeat that?
So you mentioned that you can download compiler for WebAssembly in 5 megabytes, but wouldn't it make more sense to precompile shaders before pushing to website?
We expected that that's the common use case for web developers. It was of interest to us because we wanted to build a playground, and obviously that requires the compiler. If there were other situations there where you wanted to provide some availability for someone to live edit a shader, then that might be of interest to you. I know that the web is not the only place that has binary size constraints, but it's still basically compared to some of the peer compilers, we're pretty small. So it was just kind of exciting to me that I have a bit of a background in the web, so it was exciting to me that we were able to get that small.
Yes, thank you.
So I saw that you say a developer could be a committer. So I'm curious about how a developer could be a committer and how a committer could be into the roadmap decision making or as that. Thank you.
The process of becoming a committer is similar to other open source projects. Essentially, you establish a track record of solid pull requests and potentially even feedback on other people's pull requests. And once you have a bit of a track record, then you can be nominated to be a committer by an existing committer. And you can come on the Discord and talk to our existing committers to express your interest in becoming a committer. And basically, it's very similar to, I think, one of the models that we've used for our community structure is the Chromium project. So essentially just make some commits, and once you're a trusted committer, or once you're a trusted contributor, then you can be nominated as a committer.
Yep. You see this question over
here. So I have a fairly sizable code base in GLSL for ray tracing. There's both ray tracing pipelines and ray queries. So what would be the migration pipeline, or like how would I migrate to Slang, and what kind of issues would you anticipate I would have?
So migration to Slang from GLSL, I believe essentially there's an option you provide to the Slang compiler to tell it that you're submitting code in GLSL syntax. We haven't had a ton of people who've migrated by that path, so the specific problems you'll run into probably are going to be possibly unique to your code base. but we're generally able to accept most GLSL syntax. There's not any big hurdles that I'm aware of, unlike on the HLSL side with templates.
Thanks.
Regards to automatic differentiation, when you take a derivative, you can end up with a large amount of mathematical expression, like a massive mathematical expression, which you have to simplify. How does simplification act or relate to floating point conscious operations? So divisions and whatnot.
That question is unfortunately above my pay grade. Definitely come on the Discord and ask. The automatic differentiation in Slang was the subject of one of our developers' PhD theses. So he can probably go into absurd amounts of detail about it. I have not touched the automatic differentiation code myself, so I am familiar. I can tell you how it works, or well, I can tell you the high level of how it works. I can't get into the details, unfortunately. I'm sorry.
All right. And then my second question. Typically, when you're writing a shader for, say, for example, a game, you want to do some configuration on the CPU side before you compile the shader. How does that work with Slang?
I mean, the way that you invoke the shader from the CPU side, like in general, you are going to be providing, I assume you're going to be providing a ball of Spear V or Dixel if you're using DirectX today. So you would do the configuration with the API that you're using as you do today. You can't yet submit Slang directly via the graphics APIs. You have to compile it to a format that's ingestible by those APIs. So you'd still interact with those APIs the way you do now.
Lovely presentation.
I'm wondering how Slang handles trying to do things that are just not possible in the target language.
So Slang has a capability system, which basically all the intrinsics are tagged with their availability in underlying target APIs. So when you invoke Slang, you provide it not just the source Slang, but you also tell it what your target is. And if you have source code that is not translatable to the underlying API because of a lack of capability, the compiler will return an error for you.
Sorry, one more question from me. So does HLSL backend support both DirectX 11 and DirectX 12? Because for DirectX 11, you need to use older compilers. It doesn't support some of the features of the newer language. It doesn't support HLSL 2020.
I believe the answer is yes, but I would need to double check. It should be documented on the website.
Any other questions?
Hi, thank you for the presentation. I have one question about integrating Slang as a tool or associated pipeline inside an existing pipeline. So as I understand, it's a binary basically that I can call like any other compiler. Is there, for example, a library that I could bind instead and just call it from, for example, C#?
So Slang provides a COM API to invoke it at runtime. There's documentation on the website. I don't know a lot about bindings outside of C and C++, but it is definitely possible to invoke at runtime. C# I'm unsure about.
Good generate it. That's not the issue, but generally having the library and not having to go into the source code and write the library out of it for myself. And for everybody. Thank you.
Excellent.
Very quick one. Plans to support WebGL?
So WebGL is the shading language for WebGL is based on OpenGL 3.0 or no, sorry, yes, 3.0 pre-compute. Currently, like we can generate GLSL, but it's Vulkan flavored GLSL. So I think you may run into dragons if you attempt to generate. Well, so you would be generating GLSL rather than like web flavored. So we don't currently have any plans to target any shading languages that far back in capability.
Thank you. Thank you for the presentation. As you mentioned that the Slang tries to support not just the common subset of features, but rather not every feature, but most features. As languages individually, HRSL, JSL, they evolve separately, and as they start diverging further and further, do you see that, since you say that, let's say our target is HRSL, but it's not going to compile because they're using a bunch of HRSL specific features, do you foresee that Slang is going to end up having multiple flavors of Slang and then eventually just becomes a bunch of different languages again?
So that is a good question. I think the intent is a single core Slang, and as I expect that as HLSL and Slang itself evolve, and GLSL does not continue to add new features, there's going to be more and more shaders that just won't compile to GLSL, but they will compile to Sphere V. So you can still continue to use it in the places where you might want to use GLSL, but I expect 15 years down the road, your ability to express shaders in GLSL will be diminished.
So what's the approach to shader permutations? Sorry if I missed this during the presentation, but like, does Slang make shader permutations somehow easier? Do you have specialization constants still or something new?
So I think like the main way that I'm familiar with that we're tackling shader combinatorics is the ability to use modules and link at runtime. So instead of having to recompile the entire shader for each permutation, you can, or create giant mega shaders. You can have one module that links to others and doesn't need to perform all of the original type checking and pre-computation. So it's mostly about removing redundant type checking and other front-end compiler work. I think if you're looking for a more in-depth answer, come to Discord. The shader architect, or sorry, the compiler architect can provide more in-depth detail.
Okay, thanks.
Thank you for your presentation. I have a kind of practical question. About regarding the optics. You kind of answered that the Slang already supports the optics. I had now application of optics. So is it there is a benefit if for me to transfer the optics application to into the Slang, or should I just stay into optics?
So I think I will preface this by saying that optics is the backend with which I'm probably least familiar, but I think that the benefits of Slang targeting optics are similar to the benefits targeting other targets and APIs, in that Slang still provides automatic differentiation. So if you are interested in writing code that leverages ML techniques in rendering, Slang can provide a solution for that. I am not super familiar with like I come from a real-time background, so I'm not super familiar with like if there's similar shader compilation time problems the optics side of things. But if there are, then I would expect Slang to have similar benefits there. There are definitely folks on our Discord who are more familiar with optics who might be able to give you more in-depth answers.
One question. Thank you for the presentation. The question I have is how the linking mechanism works between like when the shader compiles into the assembly and the Slang code, because you generate intermediate code, and in GPU debugger there should be ideally shown for developer as Slang code, not the intermediate one. How do you deal with that problem? In different GPU debuggers, of course.
So I know that I'm only familiar with Insight's handling of it, and I know you can follow the Slang to Spiri to SAS path there. Other GPU debuggers I am unsure about. It's definitely possible to support a similar inspection path, but I don't know.
So a quick question. So I have a course where I make students suffer the joys of GLSL. And so I'm thinking, do you think it would make sense to switch it next year to Slang instead of GLSL? Does it have like better type checking and stuff like that?
I think Slang is definitely, well, I'm biased, but Slang is a more enjoyable language to develop in than GLSL for me. And I say this as somebody who has written a chunk of GLSL. I think that it's definitely helpful for students to learn in a language that provides rich information about issues, as they type. It's also always nice when you don't necessarily have to go through a compile to get your errors. And I think also, once again biased here, but I think Slang is probably a language with a more broad growth path in front of it than GLSL. So I would probably, once again, very biased, but I would recommend Slang over GLSL for people learning shading language now, much the same way that I would have recommended Java over COBOL for somebody learning a CPU language 20 years ago.
Thank you.
When I last looked at it, there didn't seem to be much in the way of tooling for editors, IDEs like Visual Studio in terms of dealing with Slang as a sort of first-class language. But then, detection of dependencies would be handled. Are there any plans in that area rather than developers having to roll their own?
So are you talking something like the VC package system, or?
Well, so you edit a module or there are dependencies between different files and you want to compile the modules, like recompile them, but those things will change. Is that possible?
I don't know off the top of my head if this is something that's already included as part of our Visual Studio extension. I'll have to check with the authors.
I think it's
Okay. So you're definitely welcome. Please file a bug. That is something that I can bug people to prioritize. Yeah, I'm not super familiar with that integration beyond just the syntax highlighting. So maybe ask a question in the discussion forum or the Discord first, and then if people are like, oh no, they'll probably be like, but you should file a bug.
All right. That's awesome, Shannon. Thank you.